So today we will finish the rest of instruments. So let's start immediately with the telescopes. So what are telescopes? When we are using a telescope, we use it for visualization and magnification of a distant object. So it is not unusual to find that there are people who are looking for telescopes or looking inside the telescopes to see the stars or the sun or the moon. So if you imagine what is the telescope is used for, you will find out that it is used to see a better magnified image of a distant target. So again, what are the telescopes? They are optical devices used for magnification of distant objects. Can you see the slides or it is just a Cornavid? Okay. So back to the telescopes. Again, telescopes are optical devices used for magnification of distant objects. And telescopes are called a focal system. So what is meant by a focal system? A focal system means that this system doesn't cause any divergence of light rays. So it doesn't converge or diverge the light rays. So if the light rays enter this system parallel, they will emerge from it parallel as well. So they have no power. So what are the telescopes are made of? What are the main constituents of the telescopes? The telescopes in general are made of two lenses. They are separated in the air, so the distance between these two lenses could be either the difference or the summation between their foci, meaning that this is one of the main topics or main questions in the MCQ. What are the distance between the two lenses which made the telescopes? It could be either the addition or the summation of their focal length, and this is the case in case of astronomical telescopes or the inverting telescopes or what's called the Keplerian telescopes. Or the distance of between the two lenses can be the difference between their focal lenses. And this is the case in case of Galilean telescopes. And we will see this in much more details now. We have a formula for calculation of the power of telescopes. So if we have a telescope and we need to know what is the power of this system, then the power of this telescope can be named F. So it will be equal the power of the objective lens and the power of the eyepiece minus the power of the eyepiece and multiplied by the power of the objective lens multiplied by the S, which is is the distance between the two lenses. Again, if we want to calculate the power of any telescope, then the power will be the power of the first lens and the power of the second lens minus multiplication of the distance between the two lenses and the power of the first lens and second lens. So I hope that this is clear. So to have a better idea and better imagination of how the telescopes work. So all the telescopes are made of two lenses. One lens which is directed toward the object which is placed at the infinity, and this lens is called the objective lens. And then we have another lens. This lens is toward the eye, so that's why it is called the eyepiece. So, as we know, when we are looking at a far target or a far object, then the object is located at the infinity. That's why the light rays emerging from it will be parallel. So it will enter the objective lens parallel, and since this lens is a convex lens, or if it is a convex lens, then it will converge the light rays, making a focus. From this focus, the light rays will be emerging again through the eyepiece so that it will goes toward the objective lens or the eyepiece so that it will enter the eyes parallel. So that's why we are saying that the telescopes are a focal system. So the light rays enter parallel and emerge from this system parallel. So here is what's called the focal length of the objective lens, and here is the focal length of the eyepiece. So in this case, or in this telescope particularly, the length of this telescope will be the addition of both focal length of the objective lens and focal length of the eyepiece. And this is what is called the inverting telescope, or the astronomical telescope, or the Keplerian telescope. Dr. Magid is asking, where is the S? Dr. Magid, by referring to the previous formula, the S is the distance between the two lenses. So here is the distance between the two lenses. So S is not it is not present in the illustration of the optics, but it is only present in the formula. So let's review what are the types of telescopes. We have two main types of telescopes. We have what's called the astronomical telescope, and we have the Galilean telescope. It is very important in the exam to know every detail about them, and what are the differences, and what are the optics, and what are the advantages and disadvantages of each one of them. So let's start first with the astronomical. Astronomical telescope has different names. So it can sometimes be referred as Keplerian telescope, and it can be also named as inverting telescope. So astronomical, Keplerian, inverting telescopes are all referring to the same thing, which is what we will say now. So what are the optics of the Keplerian telescope, or the inverting telescope? As we said, it will consist of two lenses. These lenses will be the objective lens and the eyepiece. In this condition, or in this telescope, these both lenses are positive lenses, but with major difference, that the objective lens is weak. It is a weak plus lens, while the eyepiece lens is a strong convex lens. And this Keplerian telescope, the lenses are separated by the summation of their focal lengths. So the objective lens and the eyepiece will be separated by the addition of the focal length of each one of the objective lens and the eyepiece. So let's see this illustration. Again, if we have an object at infinity, and then in case of Keplerian telescope, it has a weak objective lens. So that in case of weak objective lens, as we know that the focal length is inversely proportionate to the power of the lens. So if the lens is weak, then the focal length will be long. So there will be long focal length of the objective lens, and this is intended. Then we have a stronger eyepiece. The stronger eyepiece, or it is a strong plus lens, that's why it will have a shorter focal length. So the focal length of the eyepiece will be short. So let's see now the illustration. Now the light rays will enter the objective lens parallel, then they will enter the lens, then they will come to a focus. This focus is far and placed at the f2 of the objective lens, like here. So this will lead to formation of an inverted real image at the principal focus of the eyepiece. Here is the critical point, because the objective lens, the weak objective lens, will form a focus. This focus must be in the same position of the focus of the eyepiece, and that's how the image will be transferred from the objective lens to the eyepiece. So here again, there will be an inverted real image formed by an actual light rays enter the objective lens, and this image will be transmitted by the stronger eyepiece to enter the system of the eyepiece, so that it will enter the eyes parallel. But the eyes cannot see in broken lines as we agreed earlier. So the eye can see only in parallel lines. So the eye will see the extension of the image, or it will see the image of this object at the distance of comfortable near vision for the eye, which is about 25 centimeters. So the eye will show or will see a virtual inverted magnified image at the infinity. So why it is virtual? Because it is formed by extension of light rays. Why it is inverted? Because of the direction of the rays. So the object at the start was inverted, and then the extension of the object was also inverted. Why it is magnified? Because the object is now is made more close toward the eyepiece, so that it will subtend the more angular magnification at the nodal point of the eye, so that it can will be magnified image, and thus we transferred an image of object at infinity to be a virtual magnified image to be seen by the eye. So the light rays enter parallel, emerged parallel, but the telescopic system enabled us to see a magnified image of a distant target. So this is the principle of telescope. Again, if we are checking for the moon, then the light rays from the moon enter parallel into the objective lens, which is a weaker plus lens that has a focus which is away from this lens, and this focus will form a real inverted image, which is present at the same location of the focus of the eyepiece, which is a stronger eyepiece that is now can make will transfer this image toward this eyepiece, then so that it will enter the eye parallel, and then the eye will see an image for this target, which is a virtual and large or virtual and magnified image at infinity. So how can we calculate the magnification produced by the inverting telescope? This can be done through many ways. It can be either the angle subtended by the image divided by the angle subtended by the object, since we are talking about an angular magnification. If we remember, when we were talking about in the physical optics, or sorry, in the geometrical optics, we talked about the magnification, and we said that we have two types of magnification, either the linear magnification or the angular magnification. And we said at that time that the angular magnification is used in conjunction with instruments used with the eye. So by placing an image of the object which is smaller than the actual object, but it is very close to the eye, this object now, or this object of the moon, will subtend a larger angle at the nodal point, and that's why it is seen magnified. Also, it can be the magnification is equal the focal length of the objective lens divided by the focal length of the eyepiece. So it will be the division of the larger over the smaller. So the focal length of the objective lens is much larger than the focal length of the eyepiece. Or it can be in the term of power. So it can be the power of the eyepiece divided by the power of the objective lens. So again, it is the larger divided over the smaller. So it will give a value over than 1, and that's how we get a magnification. So what is the advantages of this system? What are the advantages of being or having an astronomical telescope? One of the major advantages is that it causes a larger visual field than the Galilean telescope. So the field that we can see through the astronomical telescope is better and larger than the Galilean telescope. But it has also disadvantages. One of the major disadvantages that it produces an inverted image, as we just saw. Also, it has a bigger size than the Galilean telescope, because that the length of this system will be the summation of the focal length of the objective lens and the focal length of the eyepiece. So it will be a lengthy microscope. So how can we get rid of these disadvantages? The bigger size cannot be overcome because this is the principle of the astronomical telescope, but being an inverted image or having an inverted image can or has a solution. Let's see. So the Keplerian telescopes have both plus objective lens and both plus eyepieces. That's why the length of the microscope will be the summation of both of focal lengths. But its main problem that it produced an inverted image, and that can be overcome by putting an erect lens or a prism in order to make this inverted image erect. And if we did this, then this is called the terrestrial telescope. So what is the terrestrial telescope? In terrestrial telescope, it is based on the principle of image construction by convex lens when the object is present at double f, or the double focal length, or if the object is present at the center of curvature. So if you remember from the geometrical optics, we said that if we have an object present at the C, or the double focal length of a plus lens, then where is the image located and what are its characters? So we have parallel light rays that will pass through the focus, then we have a light ray that will enter through the needle point, and then both of them will meet again at the double f. So it will produce an image again present at double f, and this image will be of the same size like the first image. It will be inverted and it will be real. So basically, the only change that happened here, that it is inverted. So if we place an object at the double f of a lens, then it will produce an image at again a double f, but it will be inverted. So let's use this principle in the terrestrial telescope. So if we have the object at infinity, and this is an objective lens, and this is the eyepiece, so light rays will enter parallel, then they will meet at the focus. But now this focus will not be the same focus of the eyepiece. So let's know what will happen next. It will form an inverted and real image, which should be or must be located at 2f of an additional lens that we will put in the system. So in terrestrial telescope, we add an additional lens, so that this lens will be located between both the eyepiece and the objective lens, and the image of the objective lens will be placed at double focal length of this additional lens. And that's why when the light rays will emerge from through this additional lens, they will invert the image. They will invert the image by making an erect real image present at double f of the additional lens. So here we make this image which was inverted, we make it now inverted or erect. And this 2f of the additional lens will be the same like focal length or the focus of the eyepiece. So that when the eye is checking for the image is now virtual and erect and magnified at the infinity. So instead of having a virtual and inverted magnified image, we have now a virtual erect and magnified image in case of terrestrial telescopes. This is by the virtue of adding an additional lens between both the objective lens and the eyepiece, so that the image of the objective lens will be placed at double f of the additional lens, and the focus of the eyepiece again will be present at the double f of the additional lens. So the additional lens will not affect magnification. This is for the MCQ. Additional lens doesn't affect magnification because the image of the objective lens is present at 2f of the additional lens. So this is very important. Although that telescope itself causes magnification, but this is by the act of both objective lens and the eyepiece, but not because of the additional lens. The only value of the additional lens is to make it an erect image. What is the unclear, Dr. Magid? So since the lenses or since the image or the object of the additional lens is placed at double f, as by the rule of construction of images that we will discuss in the geometrical optics, the properties of the image produced of this additional lens will be again at the 2f, so it will be at the same distance separated from the lens, and it will be real as it is formed by an actual image, actual light rays, and it will be of the same size. So this is just geometrical optics that we discussed earlier. And the characters of the image size will depend on the characters of the distance of the object from the lens. If the object is present at double focal length, then the image will be at the double focal length of the same size. Please refer to the lecture of the geometrical optics on this topic. The magnification will be have the same rules, so it will be the angle subtended by the image divided by the angle subtended by the object, or the focal length of the objective lens divided by the focal length of the eyepiece, so it will be the larger over the smaller, or the power of the eyepiece divided by the power of the objective lens, which is again the larger divided by the smaller. So what are the disadvantages of this system? It is a very long telescope because we have now an objective lens and eyepiece and another additional lens. So these all mounted over the tube of the telescopes. So we need a lengthy telescope. This was overcome in the Galilean telescope. So what is the principle of Galilean telescope? The Galilean telescope is made of two lenses, again the objective lens and the eyepiece, but now we have difference. So the objective lens is a weak plus lens, and for the first time we will see that, or we will say that the eyepiece has a strong minus lens. So we use a minus lens in the eyepiece. This is very, very important. So a telescope can have both plus lenses, or can have both plus and minus lenses, but it never consists of both minus lenses. And the focal length or the length of this telescope is short because the lenses are separated by the difference in their focal lengths. So unlike the inverting telescope, the Galilean telescope will be the lenses are separated by the difference of their focal lengths, and let's see how is this formed. So here is the eye, and here is the objective lens. The objective lens is a weak plus lens. Let's say, for example, it is a plus 10 diopter. So where is the focus of a plus lens of 10 diopter? Would you please tell me? Yes, that's right, Dr. Shadi. It will be at 10 centimeters. So the focal length of the objective lens will be at 10 centimeters. So what happens next? Then we will have an eyepiece, and this eyepiece will be a concave lens. This concave lens will be a stronger minus lens. Let's say, for example, it will be minus 20 diopters. So where will be the focus of the minus 20 diopters? Yes, exactly. So it will be at 5 centimeters. So the focal length of the eyepiece will be at 5 centimeters. So what happens now, or what is the principle now of this Galilean telescope? As you can see that the difference between the two systems or the two lenses will be the difference in the focal length between the objective lens and the eyepiece. So the length of this telescope will not be long because it will be this is the beginning of the telescope or the one end of telescope, and this is the second end of telescope. So only the length of this telescope will be 5 centimeters. So instead of being 15 centimeter, if we add the objective lens focal length and the eyepiece focal length, it will be only the difference between their focal lengths. So what is the principle? The principle that the focus of the plus lens and the focus of the minus lens should coincide, meaning that the f2 of the convex lens, which will be located behind the plus lens, and the f1 of the concave lens must coincide in order for this telescope to work. So let's see the construction of image. Here we have the objective lens and here we have the eyepiece. So the objective lens will bring the light rays from infinity to its f2. So since we agreed that the focal length of this lens is 10 centimeters, so will be the focus of the plus lens. So the light rays should be take or this plus lens or this objective lens should make the parallel light rays coming from the infinity come to a focus at 10 centimeters. This would have happened unless if we have this eyepiece. So this eyepiece come across the light rays pathway. So this eyepiece will take this converging light rays and will make them parallel. So this is because this minus lens or will make a divergent light rays of the virtual object formed by the convex lens to emerge parallel, because that the f2 of the convex lens and the f1 of the concave lens coincide. So if this will be the f1 and the f1 of the minus lens, this is the point at which when the light rays emerge from it at end and with it will when the divergent light rays enter into the concave lens, it will be making or it will be made parallel, so that the virtual or the extension of these light rays will be made at an f1 of the concave lens. So the principle of this system that it will make it will take the divergent light rays, or sorry, it will take the convergent light rays made by the objective lens to be parallel and enter the eyes parallel, so that the eyes will see an image as the extension of light rays, and this image will be formed virtual, erect, and magnified image at the infinity. So let's again let's repeat this again. So if we have in the case of Galilean telescope, we have a plus lens. This plus lens is called the objective lens, and we have another minus lens, which is a stronger lens present called the eyepiece. The objective lens will bring the image from infinity to its posterior principal focus. This would have been the case if it wasn't for this eyepiece, because this eyepiece it is present in a position where its f2, sorry, the f1 will coincide with the f2 of the objective lens, so that it will both have the same focus. That's why when the convergent light rays enter through this minus lens, they will emerge parallel, so that they will make the light rays divergent, and by making them divergent of this convergent light rays, meaning that they will emerge from this minus lens parallel. So as you can see that the light rays enter the system parallel and emerge parallel. That's why we say that the telescopes are a focal system. And the eyes will see the image at the extension of light rays. It will be forming a virtual large or magnified image at an erect at infinity. This is very important as it produces erect image. So it will produce an erect image like the terrestrial telescope and unlike the astronomical telescope. So Please don't forget that the Galilean telescope will produce an upright erect image. The magnification again will be have the same rules, so it will be the angle subtended by the image over the angle subtended by the object, or the focal length of the objective lens divided by the focal length of the eyepiece, or the power of the eyepiece divided by the power of the objective lens. So what are the advantages and disadvantages of the system? The advantage is mainly that it can produce a large and erect magnified image. So having an erect image, this is very important, and will make us don't need the terrestrial telescope or don't need extra devices in order to make the inverted image erect. And also the main advantage is its compact and light system. So as we said, it is a very short and smaller system because the length of this system will be the difference in focal lengths. That's why it can be mounted over telescopes or mounted over spectacles. So it can be used on spectacles. Dr. Magid, object length is now in the F of the eyepiece. Yes, so the object, you mean that the objective length focus coincide with the eyepiece focus. So that's right. The disadvantages of this system that it has a smaller field. Since it causes a higher magnification, we agreed before that the magnification is inversely proportionate to the field. So if we have higher magnification, then we will have a smaller field, and vice versa. And also the object need to be held closer to the eye because it will cause higher magnification, and in such condition the depth of focus will be decreased. That's why we need to hold the object more close to the eye. We have several applications for the Galilean telescopes, and this is again important, so please remember it because it's asked in the MCQ. One of them we have just referred to it in the Affikia lecture, and we said that we will discuss it in the instruments. And here we come to its place. So we said that the magnification of eye or the magnification of spectacle in case of a spectacle correction of Affikia can be explained by the theory of by the rules of Galilean telescope. And how is so? If we have an Affikia, let's say, for example, that the power of the emmetropic eye is plus 60, as it is calculated from the Goldstrand eye and from the schematic eye. So if we have Affikia, or if a patient has Affikia, then the power of this eye has decreased. So the power of this eye has decreased the power of the lens. So that we can the eye the lens, let's say that the lens power is 20 diopter, so that the power of the eye is plus 40. So the eye is considered a high negative lens of minus 20 because the eye decreased of its power of minus 20 because of this lens removal. So the eye can be considered as a high negative lens. And if we put correction, or if we put spectacles in front of the eye, the spectacle will be about plus 10 or plus 12. So that the power of this spectacle, or it can be considered a positive lens, which is weaker. So if we have a weaker plus lens, which is present close to the object, let's say this flower, we can see this flower in front of this eye lens. So this can be considered as an objective lens. And the optical system of the eye can be considered as a high negative lens because it is aphakic now. So it will be considered like minus 20. And in order to know what is the power of this eye, or what is the magnification power of this system, we can consider it like a telescope. So just to put it in a telescope, and this will be the objective lens, and this will be the eyepiece. So the power will be the objective lens power divided by the eyepiece power. So this will be the one of the theories that will explain the magnification of effect of the spectacle, which will be about 30%. Another application of the Galilean telescope will be in case of high myopia with correction. High myopia with correction. So if we consider this eye is high myope, let's say, for example, that again that the normal emmetropic eye power is plus 60. Consider that this eye is about plus 80 diopter. So this is a very high myope, so that the eye can be considered like a high positive lens. And in order to correct this eye, which has a very high positive lens, then we need to put a minus lens. This minus lens should correct the whole plus 80, and then so that in such condition we have this eye has plus 80, and the eye should be plus 60, so it increased the plus 20, so that we need to add minus 20 diopter of minus lens in front of this eye in order to correct the image or to correct this high myopia. So the eye has a plus 80 diopter power, and it can be considered as a high positive lens, and the minus lens is considered as a weak minus power, which is minus 20. In such a condition, this can be considered as an inverted Galilean telescope. So instead of having a high minus lens and a weak plus lens, then we have the reverse. We have a weak minus lens and a high plus lens. So this can be considered, or the magnification of this system can be considered as an inverted Galilean telescope. The third application of the telescopes, apart from the theoretical knowledge or apart from the theoretical explanation of optical principles of magnification, it can be considered more practical wise. So it can be mounted over spectacles for telescopic spectacles. We said that in the low vision, we said that the Galilean telescopes can be mounted over glasses in order to increase magnification, so that it will improve the low vision for patients with low vision needs. Also, the focal system that we mentioned about it more than once can be also considered like an application of the Galilean telescope, meaning that by a focal lens, we mean that we have a lens that has no refraction but only magnification. And we said that it can, or historically it is used for the treatment of anisoconia. So how can the afocal lens be an application of the inverted or the Galilean telescope? Since the afocal lenses are doesn't have any power or doesn't have any refraction, they can be made of concave and convex surface, so that they cancel each other. So for example, if we are looking for a target, and this target will subtend an angle at the eye so that it will cause a magnification at a certain limit. If we put a focal lens, this afocal lens has a plus lens and a minus lens, both will be of the same power, so that this system will have no magnification. So it will be act like a parallel plate of, so it will have no refraction. So it will act just like a parallel plate of glass. This parallel plate of glass will cause increase of the angle subtended at the eye, so it will cause increasing magnification without actual change in the refraction. So the afocal lenses can be described or can be explained by the theory of having a plus lens and the minus lens, so that they can be also an example of the Galilean telescope. So in case of Galilean telescope, we said that the concave lens will be a bit larger than the convex lens, so that in such condition we can make the concave larger than the convex surface in order to have a magnification, but we should note that this system will have no refraction. So it will cause only magnification but no refraction. The Galilean telescopes is incorporated in different instruments, so it has is an important value in major instruments used in ophthalmology, like a slit lamp, like the telescopes, and like in opera glasses. So that in the slit lamp we have this magnification knob, and this magnification knob is based on the Galilean telescope, as we will say now in the slit lamp lecture. Also, the operating telescope, if the surgeon needs a more magnified image, then he can mount can mount Galilean telescopes over his spectacles in order to have a better magnification of a distant view of his surgical field. Also, they can be used in the opera glasses, so that if someone of the crowd sitting away from the stage, he can see the actors clearly with magnified image, although that they are away or they are far from him.